We'll be talking about black holes today. So before I talk about black holes, I want to give you guys a little bit of background. I have something behind my head that I'm going to show you, but for now, let's take a look at this. I'm sure you've seen images like this before. What this surface represents is space, except this is one dimension. I mean, two-dimensional space, right? It's like a sheet of space. So can you imagine like a whole bunch of sheets on top of each other, making it three-dimensional space? This is the way it's been represented since the time of Einstein. But I do have a three-dimensional space and a mass changing the shape of three-dimensional space for you. You're not going to see that very often. Probably this is the only time in your life you're going to see three-dimensional space changed by the presence of space and time. So, let me do this actually. Let me stop this real quick and show you guys something in the background. Can you guys see that? Can you read that, or should I put my other camera on there? It says general relativity, right? General relativity, mass curves space and time. Excuse me. So, in the presence of mass, space and time curve. That's what it's saying, right? Mass, curve, space, and time. So that's general relativity. That's what Einstein published in 1915. Yeah, just before the war, before the First World War, right? All right, so that's what it is. So we have mass here, right? These are masses. This yellow thing, this brown thing, and this red thing are masses. Yellow thing is the most massive. The brown thing is less mass. The red thing is the least amount of mass. So just the presence of mass. If you have just one proton, right, you're curving the space and time. That's it. So you're curving the space and time? Yes. Presence of mass and the curvature of time and space are easier if I explain the curvature of space first, then the curvature of time. So here's the curvature of time. Space. Now this is a massive object and it's curving this space a lot, right? Whereas if you have a little tiny mass, you're not curving it as much and you're curving it more with a medium-sized mass. So, question is this. I'm going to ask you guys a question. Can I ask you a question, Justin? Simple question? Thanks. So, why aren't you flying into space right now, Justin?
Because gravity is holding us down?
Thank you very much, Justin. That's exactly right, because gravity is holding you down. So what is exactly this thing we call gravity? Because according to Newton, gravity is a force that is holding you and pulling you down to the center of the earth in this case, right? But I'm here to tell you that gravity doesn't exist. Huh, I'm sorry. So what is instead of gravity? We have something called the curvature of space, which means because there is earth below my feet, the space that you see here on top of my head is curved. So normally I can show you one slice of space so you can see space is pretty flat. But when you get close to mass, in this case the earth, space is curved like this. Like this. And it's shoving me towards the ground. So it's nothing that's pulling you to the earth. It's just that the space that surrounds the earth is curved. And so for that reason, you can't fly into space because you're being shoved towards the ground by the curvature of the space surrounding the earth. I hope that makes sense. No. If we look at the next picture, we can see a three-dimensional shape of the same. So here's a little ball, and this little ball is curving the space around it. Now notice that the space is being curved towards the mass, right? So what if we had a three-dimensional space and then a ball moving in three-dimensional space? Now how does the shape of space change? That's what I was going to show you. And so there it is. That's how the space changes shape by the presence of the ball. So every time you move in space, you're changing the shape of space like that. Now, if you change the space infinitely, right? If you have infinite curvature of the space and time, then what you have is a black hole. So when does that happen? When you have, in a star, anyways, when you have more mass than 3 times the mass of the sun, when the core of a star is collapsing after the supernova, and you have 3 times the mass of the sun, you will curve the space so much that you will be curving it infinitely. So what happens if you change it infinitely? So now you have 3 times the mass of the sun, and it's still shrinking, and now it tore up a hole in space. It tore up space, right? Like tearing up a sheet of paper. It put an actual hole in space. So in this case here, you can go through this space if you could, but you will die before you even get there, right? So let me show you a little more now. Allow me to change this to something that is a little different here. Now here is the curvature of time. Time is also changing, right? So this is called tarmac, right? The tarmac is where the airplanes land and take off and stuff. And let's pretend we have 2 atomic clocks. One atomic clock is on the ground. One atomic clock is 10,000 feet above the ground. All right, we'll just pretend. And it's a German airplane. It's a Lufthansa. All right, so now we have 2 atomic clocks, one in the airplane and one on the ground on the tarmac. The only difference between them is that one is above the ground and one is in the airplane. Now, if you look at the times, you can see that the time is ticking just a little bit faster in the airplane. It's 2:38. Here is 2:37 on tarmac. I'm exaggerating so you can see it. Otherwise, it doesn't really matter, but I'm exaggerating. It's not really that much of a change. Something like a billionth of a second, all right, like that. So if you move from the surface of the Earth, because on the surface of the Earth, the curvature of space and time is maximized, right? The only way you can even get more if you go inside of the Earth. But here on the surface of the Earth, gravity is curving the space surrounding the Earth. But it's not just this space, it's also curving time. I can't show you curved time. This is the only way I can show you the curved time. So this is 1437. This is going faster. That means time slows down in the presence of mass. Because this guy is closer to mass, it's going a little slower. In fact, when you get to a black hole, like that black hole that I just showed you, now time stops completely. And I mean completely. Every other clock is going, but the clock at close to a black hole stops completely. So now, what if you took an airplane and you didn't quite go right next door so you can, be sucked into the black hole, but you just kind of orbited the black hole. You just orbit the black hole for a couple of days, and then you go back to Earth. What's going to happen? Well, what happens is that now you've moved in time. You have time traveled. You'd be 2 days ahead of everybody else, right? So now, because you're orbiting the black hole, and at the black hole, time is stopped to zero. So a little farther away, time's still going very, very slowly, but time on Earth is passing normally. When you get back to the Earth, you'll be a couple of days in the future. So that's how you can actually travel in time. You can go into the future, right, by just orbiting a black hole. Can you move back in time now? That's another question. It doesn't seem possible. Why doesn't it seem possible? Because if I go back in time, what happens to me, Noah? If I go back in time, right? If I go back in time, like 10 minutes ago, like where were you 10 minutes ago, Noah? I can't hear you because your sound, I think, is off.
In 1 second.
There you go. Now you're good.
Can you hear me now?
Yeah, I can hear you now.
All right. 10 minutes ago, I was in my kitchen cooking breakfast.
Let's see if you can think again. 10 minutes ago, you were thousands of miles away from here because the
Okay.
Earth was going around the sun. You forgot about that. And the Earth was also rotating. So if you traveled in time, you'd be in the Pacific Ocean now. And also in space too, right? You'd be in space. So you'd be dead. So you can't really move back in time. If you're going to move back in time, you have to move back in space and time simultaneously, right?
Mm.
Do you see that? Yeah,
Yeah.
so traveling in the future, that's a different story. So that's a possibility. You can move into the future, but you cannot move to the past. In fact, every time you get on the airplane, you go on a long trip, you travel into the future. Fraction of a second, but you still travel into the future. Because it's not just a mass that curves the space and time, it's also speed. If you travel as compared to people that are not traveling, because you're moving, time also dilates. So that's kind of weird too, right? Time
So
actually
do you think it's actually possible to orbit um the the black hole and actually travel through time? Like, is it possible,
yes,
or without
it
getting
is.
sucked in? Like, how
Yes.
would you?
Yeah, it is. Because all you need to do is to get a fast spaceship, don't get too close to the black hole, stay a little farther out, and just go at the speed that is required to orbit the black hole. So that's a doable thing for sure. Yeah, so that's how you move in time. All right. Now I'm going to get on the board and show you guys the guts of the black hole. All right. So it turns out that we can actually see a black hole by looking at a black hole silhouetted against light. We actually took images of it silhouetted against light, so it's possible to see it. All right, now let me change cameras and get on the board for you guys, and I'm going to show you guys what this is all about. All right, I think that's good enough, right? All right. So if you didn't write down general relativity means mass, curve, space, and time, so please go ahead and write it down. So now, remember we had leftover, we had a supernova, right? So the supernova, the core of the supernova was collapsing. And as the core collapsed, the upper layers went, oh, there's nothing below our feet. So the upper layers crashed towards the core. And as the core was also collapsing, they ricocheted off the core and they went explosion, right? That was a supernova. Now, if you have more than 3 times the mass of the sun left, and that's minimum, you need minimum 3 times the mass of the sun left after the supernova. So then after the supernova event, if the core has more than 3 times the mass of the sun. Now, this is the way we write down 3 times the mass of the sun, but I'll also write it down for you. Say, right here, 3 times the mass of the sun, right? Then, so from now on, if you don't mind, I'm going to write down this. 3 times the mass of the sun. Instead of writing 3 times the mass of the sun, this is a symbol for the sun. 3 times the mass of the sun. Then the core will collapse to become a black hole. I'm going to write down infinite density. We don't really know what that means. What does it mean? Infinite density. In other words, what it's saying is, what is density, right? Density is when you have, say, a cube here, and inside of this cube, you have some mass, right? So let's say you have a whole bunch of particles in here. So the amount of particles you have in this volume of space is called density. That's all. So now, when you say infinite density, how could you get infinite density? Well, not that difficult, actually. What if you had no size? If you have no size, then one particle will give you infinite density, right? So that's what it's talking about. So black hole is just this one single dot. Single dot, by definition, a dot, when the Greeks invented geometry, they said that a dot has no dimensions at all. In fact, they said this is one dimension, right? A line is 1D, one dimension. The surface is 2D. Then a volume is 3D, right? So what is a dot then? How many dimensions does a dot have? The dot doesn't have any width, doesn't have any height, doesn't have any depth, nothing, right? It's a dot. So that's what the star's core is going to continue to become, a single dot. And that's why it's infinitely dense. So I'm going to write down here, I'm going to write down this point here. It's called singularity. So singularity is a point, with infinite density. Right? So the Earth is like 5.4 grams per cubic centimeter. That means if you have a sugar cube of the Earth, you average, like you put the whole Earth in a blender, you blend the Earth, and its average density is 5.4 grams per cubic centimeter. So every sugar cube of the Earth will be 5.4 grams. Like that, right? So the Earth is kind of heavy. This guy here is infinitely dense. Now, in this case, let's say if the star's core had 10 times the mass of the sun, that thing has 10 times the mass of the sun. So it has mass. What else does it have? So we say it has one mass. Now, it must also have rotation, because the original thing, the original core, must have been rotating. All stars rotate. So this guy must have also rotation. Rotation.
Professor, are you referring to the dot?
Yeah, the dot must have
The
rotation.
The dot has how many times more mass than Earth? Or than the sun, I'm sorry.
Well, in this case, we have one that has got 10 times the mass.
Okay,
But we said if
10
it's got
times.
3 times the mass of the sun, it's going to become a black hole. But if the core has 10 times the mass of the sun, it's going to be even a more massive black hole. You just
Got
need
it.
to go over the 3 times the mass of the sun limit. That's all.
Thank you.
You're welcome. So, but it also has charge. And that's all that we know about it. Why does it have charge? Because, it's made of protons and electrons and stuff. So it's either positively charged or negatively charged. If it's got more protons, it'll be positively charged. Regardless, it has a charge. And that's all that we can say about this. It has mass, rotation, and charge. We don't know if it's made of peanut butter. We don't know what it's made of. We don't know the chemical composition. Nothing. This is all that we know about the black hole, right? We also know it's infinitely dense. So he said, according to general relativity, it curves the space and time. This guy curves the space and time. It curves it all right, but infinitely. So there is a sphere surrounding it. Some kind of a sphere here. Let me see if I can make it into a sphere. Right, so there's this sphere. This sphere is called the event horizon. The event horizon is the limit where that little dot has curved the space around it infinitely. Not just the space-time as well, right? So I'm going to say this is called the event horizon. So inside of here, we're going to say, see if I can find a place to write it. This is, I'm going to say inside, space and time are infinitely curved.
Inside the dot or sphere?
There is no inside the dot. The dot doesn't have inside, right? There's no inside. There's nothing. It's a dot, right? It doesn't have any width. It doesn't have any length. Nothing, right? It's a dot. It's a point. So a point doesn't have any dimensions. So we're talking about this event horizon, this sphere, right? So space and time are curved infinitely. Inside of this sphere. Like that. So
Would we
space,
also say inside the event horizon?
yes. So there's a
Thank
sphere
you.
here. It's an imaginary sphere. It doesn't exist, right? So inside of the sphere, we say space and time are curved infinitely. Remember, what's his name was saying that it's a point of no return. The other guy says, no, it's not a point of no return. It's a sphere of no return. So whichever, it doesn't matter. Regardless of what they said, this is a black hole, right? So a black hole has an event horizon that surrounds it, and that black hole's event horizon represents the limit of where space and time are curved infinitely. So outside of here, it's not curved infinitely, right? I'm going to write that down. Not curved infinitely. Infinitely. Out here. Just inside of here, right? Now, what's happening in there is space is falling into that singularity. And space is falling into that singularity faster than light. So here's space falling in faster than light. So space is falling in faster than light. All right? Space is falling in faster than light. You might say, wait a second. I thought that nothing can go faster than light. It turns out that space can go faster than light. So the only thing that can go faster than light is space itself. So space can go faster than light. You can maybe make a bet with somebody. You're always going to win. You're going to say, "Whoa, I know something that can go faster than light." You go, "No, it's impossible." Well, space will fall in faster than light. So now, I'm going to go inside of this black hole because I'm a super astronomer. The super astronomers are not scared of black holes. In fact, they will survive black holes. So don't try this at home. Only astronomers can go inside of a black hole. And I want to take my cell phone with me. So here's me.
So it's the sphere that is the black hole?
Well, that's a good
Or
question,
the dot?
right? They're both black hole, the dot and. So I would call the dot, which has the mass, right? That's the guy that has all the mass. This is the guy with the mass, right? So this is the mass. This guy has the mass. The singularity has the mass. The sphere is a sphere of no return. It's a sphere where the space is falling in faster than light, and the space and time are curved infinitely inside of this sphere. So you can call either one of them black hole, right? Some people call the singularity black hole. Some people call the space that surrounds it black hole, just like you saw that in that movie, right? The two scientists there, one of them called it the dot is the black hole. The other guy said the sphere is the black hole. Regardless. So now, what's going on here? Well, as you get closer and closer, time basically stops here, right? So when you go inside of here, time is completely stopped, right? But what I'm going to do, I'm going to call 911. I'm going to say, I'm stuck in a black hole. Please help, please help. So I took my cell phone with me, 5G, and I'm going to send the signal now. So I'm calling him. Somehow I survived. I shouldn't have survived. I would have been dead by now. But I survived because I'm an astronomer. So now I'm going to send the signal out. Well, as soon as I send the signal out, it's going to go directly to singularity. Nowhere else to go. That's the only place to go. Because the space is falling in faster than light. My signal is only going as fast as light. So my signal can't get out. That's why light can't get out, because space is falling into the singularity faster than the speed of light. Nothing can escape. You have to go faster to escape. So somehow, if you have a spaceship that goes faster than the speed of light, maybe you can make a trip into the black hole and get the heck out of there. Maybe. That's for the future.
Professor?
Yes.
To clarify, time is completely stopped inside of the event horizon, and then that signal would get dragged back to the singularity.
Yeah, because the space is falling in faster than light. My signal is only going as fast as light, so it's going to carry it right into that singularity.
Thank you.
Yeah, but I should have been dead, right? Why am I dead? Well, I should have been dead. So how do you die once you get close to this black hole? Right? How do you die? Well, this is how you die. This is me again. And I'm very, very close to this black hole. And now, normally, we don't really care. Like I'm standing here right now. I don't feel like the earth is pulling my feet any closer than my head, right? It's about the same because I'm only 6 feet tall, so I'm being pulled by the gravity. If you think of gravity as this pull force. So here, my feet are being pulled in pretty hard. I'm pretty close. My head is also being pulled in, but not as hard as my feet. My feet are closer, so my feet are being pulled in a lot harder than my head. So what happens to me is I'm going to become spaghettified. Spaghettified means I'm going to be a big, long spaghetti. Now, I don't know why I changed my color. I should be a blue spaghetti, so I'm going to be...
It'd be like putting you on the rack.
Yeah, exactly, right? So now I'm going to be spaghettified. These are my atoms as I fall in. So this is an actual technical terms in astronomy. The spaghetti, let's see, let me spell it correctly. I think spaghetti is G-H. Spaghettified. Spaghettified. I'm going to be spaghettified. So why am I spaghettified? Because my feet are closer, so they're being pulled really hard. My head is kind of like left behind, so not being pulled as hard. So the difference between the tidal forces between my feet and my head makes me stretch like this, and I'm going to die as a spaghetti. Now, this is the thinnest spaghetti you've ever seen in your life, right? Incredibly thin spaghetti. All right, when you guys have finished this, if you would like to take the notes, and then I will proceed. So next, I kind of like to show you guys what the deal is with Interstellar, right? Interstellar. You guys have seen Interstellar?
My favorite movie ever.
Okay. So now I'll explain to you guys What happened in Interstellar, and what's the problem with those theories in Interstellar? So remember, black holes have these three things: mass, rotation, and charge, right? So the one that I just drew for you, that one has mass, but it has no charge or rotation. We didn't talk about charge or rotation, right? So I'm going to give you a version where it's a reality. Reality is that black holes should be spinning. So let's make a black hole that does spin. Can I erase this? Any objections?
Yes.
Yes.
It's okay, you guys?
I'm done.
Excellent. All right. So now let's make a realistic black hole. Realistic black holes have two event horizon, not just one event horizon. So let's give you that. But before I do, let me ask you guys a question. How many ways in space can you move?
3.
It turns out there's 6, right? So I can go forwards, backwards, I can go left, I can go right, I can go up, I can go down. So that's 6 different ways. It's called 6 degrees of freedom. So you can move 6 degrees of freedom in space, 6 different directions, right? But I can also move in time in the black hole. That's the place I cannot do anything in time right now. I can't go to tomorrow. I want to go to Friday, man. I don't care about Tuesday. I want to move. So we can't really move in time. But here, you'll be able to move in time. So let's see. Now, when you have a rotating black hole, you have something called a rotating singularity. So now you have a rotating singularity. So here's a rotating singularity. A rotating singularity has something called a ring singularity. So you have a ring singularity here. Now, if this ring singularity didn't have any event horizon, you could see it kind of like a TV set, like a round TV set going by, like you're watching it in the stadium. It'd be like a big giant TV set going by. And if you looked at it, you could see stars in space and time. You could see stars maybe from 1 million years ago and 10 billion light years away, something like that, right? Now, so let me just put some galaxies and stuff in here so that you guys will know this is a window to space and time. So you can see things that are somewhere else in time and somewhen else in time. All right, now let's put in the event horizons. So we have 2 event horizons here. One's called inner event horizon. Let's see if I can draw this correctly. So this is called inner event horizon. E dot H dot means event horizon. That's a universal symbol. And then I'm going to do one more. See if I can do this one. It's going to be tough. Okay, I did it. Yay. All right, so this is the second event horizon. So I have 2 event horizons. This is the outer event horizon, the outer event horizon. Now, I'm not going to vouch for the shape of it. It could be like an egg. It doesn't have to be spherical, all right? So let's not get into the shapes. So now, if I'm going in, and again, I'm going to be able to go in because I'm an astronomer, right? So the astronomer guy is going in, and as soon as I go in, I notice something. I notice that time and space have reversed. So time has become like space, and space has become like time. So what does that mean? That means that I can move in 6 different ways in space. I'm sorry, 6 different ways in time. That means I can go to the future. I can go to the past. I can go left in time. I can go right in time. I can go up in time. I can go down in time. But there is only one way I can go in space. Which direction is that? Into the singularity. That's the only way I can go. There's no other way. I can't go left and right here anymore. I've entered the event horizon, right? So now I can move in time, up, down. What does that mean? Like go left in time. Nobody really knows what that means, going left in time. But it's like a superpower, right? You get a superpower. You go, I can go left in time. Maybe you're sliding in different time zones or something. I don't know. But it's a superpower. So you can do that. You can move 6 different ways in time, but only one way in space. Now, once you go into the second one, time and space reverse again. So what that means is now, inside of the second event horizon, everything is normal. You can move in space, and you can't move in time, just like you did when you were outside. So you'd be just like a normal person here, right? You can move in space, but not time. Here you can move in time, but not space. So you go to the second one. All right. So that's all fine and dandy, and you can't do anything about this right now. There's one possibility, though. One possibility that Interstellar can come to pass, right, Noah? If you like Interstellar, you have to hope that this is going to happen. So what happens is, if this thing here is spinning, and when the core of the star collapses, the rate of spin goes up, right? The smaller you get, the faster you go. If the rate of rotation reaches, because when it's big, it's maybe rotating once every 28 days, like the sun. But as it gets smaller, the rate of rotation goes up. So if you're as big as the Earth now, you're rotating 100,000 times a second or some stupid thing like that, right? Or 1,000 times a second. So eventually, what happens here is, if you get to the speed of light, the inner event horizon gets bigger. As the rate of rotation goes up, the inner event horizon is getting bigger. The outer event horizon actually shrinks. So this one shrinks as you're approaching the speed of light. The outer one shrinks, the inner one expands. Only if you reach the speed of light and these two meet, like that. At that point, the two event horizons meet. And something incredible happens at this point. What happens is that both of the event horizons will disappear. There'll be no event horizons. Only if the rate of rotation reaches the speed of light. So what happens then? Well, what happens then is they both go away. So we don't even have any event horizons. So what do we have? Can I erase the event horizons? The event horizons are going away. They're going bye-bye.
And that's because the ring of singularity is spinning faster, or?
Yes. The ring of singularity, if it reaches the speed of light, the event horizons will dissipate. The inner one gets bigger, the outer one gets smaller. When the two event horizons meet, both event horizons just disappear. All right. So,
And you said only when they meet do they disappear.
yeah, that only happens when you go at the speed of light. All right, so let's make this baby go away. And everything is gone now. What do we have left? The ring of singularity is all that there is left. This is all we got. So this.
I have a question.
Yeah.
So if it takes the speed of light for the two rings to come together, does that mean that the inner event horizon is constantly expanding until it hits the outer one?
Yeah, as it's shrinking down to become a black hole. Imagine it's the very last gas of the core of the star, right? So it's already gone supernova, and the core of the star is still shrinking. And as it shrinks, it also spins. If the rate of spin by the time it becomes a black hole reaches the speed of light, then it becomes this. Now, what is this called? It's called naked singularity. So naked singularity is a singularity with no event horizons whatsoever. So isn't there a show on TV where you can actually enter a ring, right? You go inside of a ring and you move in time and space. You guys know that show?
I know what you're talking about. That's that
Yes, right? What is it called?
yeah.
They found it right next to the pyramids. Remember, it was buried next to the pyramids and all that. That's what this is. That thing in the show is a naked singularity. So now, it's still dangerous. So that movie that you saw is not realistic. You're still going to get destroyed. There's still gravity at the edge. So now if you approach it here at the edge, you die. So if you just go towards it, and if it's rotating like this, right? And you go towards it like that, you die. But you can approach it like this. You can jump in. You just can't approach it from the edge. That's all. Because there's still gravitational force there. Okay. Now, it's a ring of singularity. Now you can go in, except, according to theory, it closes down. It's only open for something like 10,000th of a second. So if you're fast enough, 10,000th of a second or 100,000th of a second, you got to get in there as fast as it forms and then go. The problem with interstellar is, let's say this did happen and it did go through it. You can't pinpoint where you're going. That's the problem. There's no pinpointing this. In fact, on the other side of this, there is the wormhole. This is called a wormhole. Right? So there's a wormhole. And now you can go in. It's all right. You're allowed to jump in. So you can jump into your spaceship. Except I don't know how in the interstellar they figured out that you can pinpoint exactly when and where you can end up. I don't think you can ever do that. Even with high technology, it's not possible. So now what happens? Now what happens is that you're going to come out. This is you now. So where are you coming out? Where is that place? Well, this is some when else and some where else. So this is some when else and also some where else.
But don't we get spaghettified when we go in the ring of singularity?
No, there's no more. There is no more event horizons. They all went away. This is naked. This is okay. You just can't approach it from the edge. This guy here is dead, but he can jump in.
So we have to wait until the event horizons have collapsed into each other and disappear.
Correct. You have to wait for the naked singularity. Right.
Okay.
You know, something interesting, the brujas. You guys know, anybody knows brujas?
Witches?
That's right, witches. So brujas in northern Mexico, right? They talk about a ring of power, that you can travel through the ring of power. I don't know what they're exactly talking about, but they talk about traveling in space and time. They're talking about like flying around the earth and things. I've just read books about it. That's all I know. Like there's a guy named Carlos Castaneda Carlos Castaneda's books are pretty awesome, especially the fourth book. Yeah, he talks to the northern Mexico. What he calls them Indians. I don't know what to call them. He calls them Indians. So, anyways, now you can also, another possibility is that you can come out in another universe, because what you've done, you put a hole, you tore up the space and time. I can't express myself strongly there. Let's see if I can get a sheet of paper. Now, imagine this was the space, right? You put a hole in it. You tore up the space. So now the space is like this. You did this to space. You're going through the space, right? Instead of going from like here to here, what you've done is you made there come to here. You curved the space, so instead of traveling in space, you can just go directly there, like that. You just went from there to there. Instead of actually traveling from here to here, you just tore it up and you went to the other place, like in Interstellar. Right? That's what you
That's
did.
like the electrons.
I'm sorry?
The electrons going from one level to another around.
Oh, you're talking about the leap.
Yep.
Yeah, okay. Yeah. It's kind of like that. Universe is just weird, right? So it could be another universe too. Now what the heck are you gonna do? Because it could be an ordinary universe, or it could be a universe where things are backwards. Like gravity could repel instead of gravity will attract you. Then all your atoms will fall apart. You could be dead as soon as you get out. So there's a lot of problems here. But I guess Interstellar fixed those problems, you know? What can I tell you? All right. I'm done with the ring singularity, the naked singularity. So I hope you guys have a better idea of what happened in Interstellar now. They just took their spaceship and they went right through the ring singularity, through the wormhole, and they came out on some other planet, some when else and some where else, right? What do they do with?
Oh, there was that one show, Terra Nova, and they went through that and they ended up traveling back in time to prehistoric time.
Ah, yeah. There's
That's
yeah.
pretty cool.
What is the other show called? Though?
I think they based it on that one because it had the same entrance loop. And there's either Quantum Leap but I think it's something else because they've had a bunch of shows on that.
Yeah,
And it's
I'll
got
let you know next
the halos on two different destinations or wherever they are, the portals.
time. Right,
I
right,
think they're
yeah.
all based on that.
I forget the name, unfortunately.
Yeah, me
Yvonne
too.
is asking, is that 4D? No, 4D is something that I will talk to you guys about it next week. Actually, we'll talk about 4 dimensions too. Fourth dimension is really weird, you guys. That's even more weird than traveling through the space here. All right. Don't be surprised if, like, you're sitting at home, all of a sudden a black hole appears. Now, you can also make mini black holes too. In fact, they're making it at Switzerland in the accelerator. They're making tiny little black holes. The event horizon of those black holes is about the size of an atom, right? That's how big black holes are.
Isn't it a bad idea to try to create black holes on the planet?
Well, here's something else. Black holes evaporate. Everything that is inside will be coming out, right? And
Oh, it
so,
sucks it up and then dissipates, kind of, right?
yeah. So if all black holes eventually will evaporate in time. So at the end of the universe, where there's nothing, is going to be, I'll talk to you about it later, but it's going to be all dark, nothing, not even stars, nothing. The last thing that you'll see are these black holes evaporating. They explode. There's huge explosions. Whatever went in, now it's going to come back out. That's called the evaporation of black holes. So I think you guys got enough about black holes today. Yeah. Oh.